Worksheet problem 18.5 asks us which of the following statements are correct. Starting with the first one, it states that Cl2 will have a higher melting point than Br. We know that melting point is a phase change from a solid to a liquid. So we're going from something with less energy to something with more energy. We have to add energy for this to happen. The intermolecular forces that are holding the solid together are what we have to fight here. The one that has the stronger intermolecular forces will have the higher melting point. So now we have to compare Cl2 to HBr. So Cl2 is a diatomic gas, meaning that this bond is entirely covalent, it's entirely nonpolar. So this is a nonpolar molecule. The only intermolecular force that's available for nonpolar molecules is London dispersion forces, which is the weakest intermolecular force. If we compare that to HBr, we know there's a net dipole because bromine is more electronegative than hydrogen, and so this is a polar molecule. So it either has only dipole-dipole interactions, or it also has hydrogen bonding. And the way to determine that is to ask ourselves, is there HFON bonds? Well, we do see a hydrogen, but it's bound to a bromine, not to a fluorine, oxygen, or nitrogen. And so since there is no HFON bonds, there's no hydrogen bonding. And what we see in this molecule is dipole-dipole interactions. We know that dipole-dipole interactions are stronger intermolecular forces than London dispersion forces. And so HBr has the stronger intermolecular forces, and therefore, like we said, should have a higher melting point. So this is going to be marked false. The next statement reads, HF will have a lower vapor pressure at negative 50 degrees Celsius than HBr. So here we're comparing vapor pressure, and what vapor pressure refers to is essentially when you have something in a liquid phase, there's always going to be some exchange of liquid to gas. There's an equilibrium of liquid going to gas and then going back to liquid right above the interface of the two phases. If something has a low vapor pressure, it means there's not a lot of gas, more liquid. If something has a high vapor pressure, there's a lot of gas. What we can determine from here is that if something has strong intermolecular forces, it's hard to go from the liquid phase to the gas phase. And as a result, it will have a low vapor pressure. So now we're going to compare HF to HBr. Looking at HF first, we see that we definitely have a dipole moment going towards the fluorine. Fluorine is way more electronegative than hydrogen, so it's pulling a lot of electron density off of the hydrogen to the fluorine. This is a polar molecule. So we have to ask ourselves, is it going to be dipole-dipole interactions, or will it be H bonding? And we can determine this again by checking for H-Fon bonds. We see here that this is an H-Fon bond. It's H bound to fluorine, and as a result, we see hydrogen bonding. Compared to HBr, which we just looked at, there was a dipole moment, but it was smaller. So it was a polar molecule, but because we had no H-Fon bonds, it's just dipole-dipole interactions. Hydrogen bonding is stronger than dipole-dipole interactions, and as a result, we would expect the molecule that has H bonding to have a lower vapor pressure. So this statement will be true. Next, the statement reads, Cl2 will have a higher boiling point than argon. So boiling point, just bringing this into consideration, is when something goes from the liquid phase to the gas phase. It needs to add energy into it, and we have to pull apart molecules that are attracted to each other by IMF. That tells us that something that has stronger intermolecular forces is going to be a higher boiling point. So we can consider Cl2. As we determined in part 1, this is a nonpolar molecule, and therefore all it has are LDF. If we look at argon, it's just one single atom, so that's definitely nonpolar, so all it has is LDF as well. In order to differentiate between the two of these, we need to consider which one has the strongest London dispersion forces. We can do so by looking at their molar masses. Cl2 has a molar mass of 70.906 grams per mole, whereas argon has a molar mass of 39.948 grams per mole. London dispersion forces increase with increasing mass, so Cl2 will have more intermolecular forces than argon. We had said that stronger intermolecular forces results in a higher boiling point, so Cl2 should have the higher boiling point. This is a true statement. Next, we look at the statement, As the polarity of a covalent compound increases, the solubility of the compound in water increases. Primarily what we're looking at here is solubility. A nice typical rule of thumb in solubility is that like dissolves like. And what I mean by that is that if something's polar, it will dissolve polar things. And if something is nonpolar, it will dissolve nonpolar things. So what we want to do here is see, is water polar? Because then we can determine if a polar compound would dissolve in it. So let's draw water. We see electron density being pulled into the oxygen and away from the hydrogen on both sides. There's this overall dipole moment. So we know it's a polar molecule. And so what would dissolve in water? Other polar things. So that's a true statement. The last statement says HF will have a higher vapor pressure at 25 degrees Celsius than KCl. So back to vapor pressure. We had talked about this before. If something has stronger intermolecular forces, it'll have a lower vapor pressure. So we want to compare HF and KCl. We've already talked about HF. We know not only is it polar, but we have hydrogen bonding because of this HF bond. Looking at KCl, we see potassium is a metal, chloride is a nonmetal. So this is an ionic bond, not a covalent bond. That's a very, very strong interaction. So that is true.